Let me just see if I can get my screen shared. All right.
Wonderful. Thank you.
Play. So you should be able to see my screen and a mouse moving across it.
Yes, indeed.
All right then.
Okay, thank you very much. So we welcome here Tessa Baker. He's a very good friend, and she's going to talk about testing gravity with gravitational waves. Thank you very much, Tessa.
Fantastic. Okay. Hello, everyone. Good morning or good afternoon, depending on where you are, or good evening here from cold and rainy London. It's a real pleasure to speak at this workshop, so many thanks to the organisers for inviting me. And as the previous speakers have said, it's a shame we can't all be together in Mexico this year, but hopefully that will happen again. So today I'm going to tell you about how we can use all the excitement of the past few years surrounding gravitational wave astronomy to test the laws of gravity on cosmological scales. And thanks to the fantastic organization of this workshop, both Jackson and Jutta have introduced lots of concepts that I needed already. So we've had a great introduction from Jackson on why we want to modify gravity, and we've looked at some of the kinds of theories that are available. And I'll focus more on the how. How do we actually do this? What are the results like with gravitational waves? So on the slide here, you might recognize that we have the first 11 events that were detected by the LIGO-Virgo detectors. And that includes 10 binary black holes. Those are the panels, the smaller panels. And the larger panel down here is, of course, the binary neutron star GW170817. And for each event, what you've got here is a spectrogram. So that's a plot which shows the spread of frequencies in the gravitational wave signal. And you can see they spike up here to higher frequencies at the moment of merger. And then overlaid on the front, you have the waveform itself. And if you look really closely, there is both a theoretical waveform and the data actually underlying it. So as previous speakers have said, this is an incredibly exciting time to be working in gravitational physics. We have more and more events like this piling up, and it's time to start thinking about what we can do with this wealth of new data. So my talk today will be in 3 parts. I'll start off giving just a brief intro to what is the status of the detectors, and I'll introduce a few thoughts about the theories as well. In the second section, I'll talk about what's happened so far. What have we learned from just the, of order tens of gravitational wave events we have in hand at the moment. And then the third and final section will be thinking more about the future. What's next? What would we like to do? And this is mainly a review talk, so I'll be covering lots of people's different work, but I might just sneak in a little bit of my own work at the very end. Okay, and on the right-hand side of your screen here, you have this fantastic, brightly colored kind of delirious painting. And this comes from the physicist turned artist, Gregor Hondesky, whose name has been mentioned several times already today. And he likes to combine his hobbies of physics and art, as you can see in the painting. Okay, so let's get started then with the first section, which is to just give a quick sort of status update on the experiments and theories. So the LIGO-Virgo detectors are currently offline. They were taken offline at the end of March this year because of the pandemic. And it was considered unsafe, of course, for people to continue working on them. Luckily, that shutdown was only about 1 month earlier than they were due to come offline anyway, at the end of their 3rd observing run. So they only lost about 1 month of observing time. And in their third observing run, or what we call O3, they found 56 new events. Okay, so you can see the rate of increase here, right? The first two observing runs found 11. Now the third observing run by itself finds 56. Okay, and they haven't fully published all the details of those yet, but there are some details available in their database. Okay, and what's supposed to be happening now is the detectors are supposed to be undergoing engineering works to make them more and more sensitive. And the fourth observing run, or O4, was originally due to start next autumn. Now, I think word on the street is that that schedule has, of course, been delayed by the pandemic, and we're looking probably more around spring 2020 now for that, but it's yet, sorry, 2022 for that, but it's yet to be confirmed. So that's what we have at the moment. But I want to briefly just look forward to the next generation of gravitational wave detectors, which are already well underway in terms of design and thinking about the science capabilities. So this will be the third generation, so-called, of gravitational wave detectors. And the time scale for this is really from 2030 onwards, okay, which may seem ages away, but that's how far you have to plan to build and get all the funding for these amazing instruments. So there are several proposals on the table, but perhaps two of the most mature right now are the Einstein Telescope, which is a European proposal. And it's got this unusual triangular configuration that you can see in the artist's impression here. So that would be a ground-based experiment. And also LISA, which is the Laser Interferometer Space Antenna. And as you can see, that's a gravitational wave detector in space. Okay, and the laser beams that form the arms are then going to, can then be much, much longer than they could be on Earth. In this case, it's about 2.5 million kilometers. Okay, and where things get really crazy is with the expected detection rate of some of these experiments. So the Einstein Telescope is expected to detect just under 1 million events per year. 1 million events per year. And this thing could easily operate for 10 years or more. Okay, so, you know, going up from 56 to 1 million, we really are looking at an era where gravitational wave astronomy is almost on a par with electromagnetic astronomy in terms of the sort of statistics and the populations we can study. For LISA, things are a bit different because LISA doesn't look at stellar mass compact objects. Instead, LISA is sensitive to the gravitational waves from massive black holes, like the ones found at the center of galaxies, which might be 10 to the 6, 10 to the 7, even 10 to the 8 solar masses. And those things are rarer and they merge less frequently. So LISA will only see about 130 of those a year, ballpark estimate, but it's still a completely new type of source. Okay, so this is the future we have to look forward to. And what I want to talk about today is how we are going to use this to test the theories, for example, that Jackson mentioned in his introduction. So because Jackson gave a really nice intro to why we modify gravity, luckily I don't have to do that. So here is my one-line summary, that cosmological extensions of GR are motivated partially by cosmic acceleration, sometimes by trying to explain away cosmological parameter tensions that are coming from various large-scale structure measurements, and sometimes, less commonly though, as a dark matter substitute. So perhaps trying to get rid of that part of the dark sector and replace it with an extension of GR. Okay, now these, I want to stress, are cosmological theories I'm talking about, and just to kind of touched upon this point as well. So the theories that I talk about today are designed to modify the weak field regime, in particular the large scales of the universe. They're not necessarily designed, these theories, to do things around black holes. Okay, There is sort of other classes of theories like the ones Jutta presented that are studied because of their strong field phenomenology. Today, we're in the weak field regime. And what that means is that we often have to build our theories such that they reduce to general relativity in the strong field regime or in very well-tested environments like the solar system. So many of these cosmological theories come with what we call a screening mechanism, which is something which, again, suppresses those deviations from GR in dense environments, say. Now, if I had another hour, I would tell you all about screening mechanisms. I don't, unfortunately, today have time to go down that road. So I'll just put the names of some screening mechanisms on the slide. There might be things that ring bells for a few of you, or you might have seen them on archive. So the reason I'm kind of carefully explaining my way around these different kinds of theories is because the theories that I will be talking about today and the tests I'm talking about focus on the propagation of gravitational waves, not the generation. Okay, so the picture you should have in your mind is that both the source and us, the observer, we're sitting in galaxies, we're sitting in nice dense environments where hypothetically a screening mechanism could be operating. And that means the sources themselves evolve as per GR. And what we're going to study is the strange things that can happen to those gravitational waves when they leave that host galaxy and they travel across intergalactic space towards us at the observer. Okay, so that's what we're talking about today, propagation, not generation. Now, in order to present some results and some constraints, I decided to focus on a particular group of theories today, okay, just because we only have so much time together. And it probably won't surprise any of you by now that the family of theories I'm going to talk about is Hondesky gravity, which both previous speakers have mentioned. Okay, and Jutta actually showed the action for Hondesky gravity. It was that big, messy action containing a scalar field. So in a nutshell, just to remind you, Hondesky gravity is the most general theory you can write down that has one new fundamental scalar field and results in second order equations. Okay, and that second order equation requirement is just a little bit of a theoretical preference because we know that tends to preserve the stability and kind of avoid pathologies in the theory. So I'm not actually going to show the full action for Hondesky because I don't need it today. So we'll just kind of write that in a cartoon form. But what we do want is to look at the linear perturbation theory that results from Hondesky gravity. So if we take the linearized field equations of Hondesky around an FRW background, so smooth expanding universe, what drops out is a set of 5 parameters. And we usually denote these with the letter alpha, so we call them the Hondesky alpha parameters. Okay, and the statement is wherever there is a term in your linearized field equations that is different from GR, that term has a coefficient that contains one or more of these 5 objects. So these 5 alphas are, in some sense, parameterizing the deviations from general relativity, at least at the level of linear perturbations. Okay, and they've got these names, alpha K, alpha B, alpha M, alpha T, and alpha H. I'll tell you what they mean in just a moment. But I need to point out to you that I'm being a bit sloppy when I call them parameters, because parameter kind of makes you think of a constant. And as I've tried to indicate here, they are in fact functions of redshift. Okay, they're functions of time. And that makes them a little bit harder to constrain. Okay, so let's meet what these 5 alphas actually do. So as I've said, they quantify non-GR behavior, but there is a kind of nice physical interpretation you can give them. So for example, alpha T, and this appeared briefly towards the end of Jackson's talk, Alpha t is a parameter that describes the speed of propagation of gravitational waves in your theory. Okay, so speed of gravitational waves we write as ct, t stands for tensor mode, and that's equal to 1 in my units, the 1 being the speed of light, plus alpha t. Okay, and alpha t could be in principle positive or negative to give gravitational waves that travel faster or slower than the speed of light. Okay, and in this particular case, faster than the speed of light does not imply causality violation, if that's kind of something that pops into your head. So we'll meet that parameter shortly. Alpha m, Jackson also mentioned very briefly. Alpha m is the effective run rate of the Planck mass. So Jackson showed this in teleparallel gravity, and it's also present in Browns-Dickey theory, which Jutta mentioned, and all kinds of modified gravity theories. They give you a time-evolving big G, or Newton's constant. And that's effectively equivalent to a time-evolving effective Planck mass. And so this alpha m parameter holds that rate of evolution of that Planck mass. Alpha b is called the braiding parameter, and it quantifies a particular mixing of the kinetic terms of your metric and your new Hondesky scalar field. Alpha k is the kineticity parameter, and it tells you whether that new Hondesky scalar field has a very sort of standard canonical kinetic term or has some more exotic kinetic structure, which can happen in some of these gravity theories. And finally, there is alpha h. I don't know why it's been given the letter H in this case. We call it often the beyond Hondesky term because it describes an extension of the original Hondesky action. And this extension of the action is reached by doing a disformal transformation. Okay, if you don't know what a disformal transformation is, it's a bit like a kind of super version of a conformal transformation. So quickly in sort of cartoon form, if you transform your metric by a function, let's call it omega squared, that's a conformal transformation. And when you have an extra scalar field kicking around in your universe, you're allowed to add this term here that contains its derivatives, and that makes it into a disformal transformation. Okay, so these 5 objects then are the 5 operators of linearized Hondesky, and they're all 0 in general relativity. And our quest then is to ask how well can we measure or place an upper bound, at least, on these objects. Okay, and if we can do that, if we can bound all 5 parameters to some good precision, either we find something interesting and we find a theory of modified gravity, or we rule them out, and then we can say that we've actually tested this big chunk of the theoretical landscape, which is all the theories that have a single scalar degree of freedom. Okay, which is not everything in the landscape, but it's a big family. So I'm going to ask you just briefly to snapshot in your mind these 2 parameters here. Okay, because I'm going to put them on one side and I'm going to come back to them a little bit later. Okay, so just remember alpha m and alpha b. And for now, we're going to talk about some of these other parameters. Okay, so we're moving on to the things we've learned so far. What has happened in this story? Okay, and it is probably no surprise to anyone that the first thing I'm going to talk about is the binary neutron star merger, GW170817. And this has been mentioned already by both speakers, so we won't dwell on it, but we'll see how the results kind of pan out for Hondesky. Okay, so I think everyone is familiar with the basics here. So you know that this binary neutron star merger was seen by LIGO Virgo, that's the middle panel, spiking up to merger there. And the top and the bottom here are the flux counts from 2 gamma ray spectrographs that were operating at the time, Fermi and Integral. And there's this coincident peak in the gamma ray flux, which was found to be completely consistent with being the start of the gamma ray burst associated to the merger. Okay, and the thing we're really interested in here is the delay between this moment of merger and the start of that gamma ray burst, which is about 1.7 seconds. Okay, so we want to use this kind of one measurement then to try and potentially constrain our alpha t parameter, which, remember, described the difference in speed of propagation of gravitational waves from C. Okay, and I've just reinstated the factors of C here to make everything consistent. So what we're doing here is we're considering that the gravitational wave signal and the EM signal set off at the same time, and they run a race basically over the 40 megaparsecs between the source and the Earth. And if they had very different speeds, they would have to arrive at Earth at a much bigger time interval than that 1.7 seconds. Okay, so you can do a really simple kind of time of flight calculation. Because the source was really nearby, it's actually, nothing too complicated. And you'll find this expression relating the time difference in their arrival to the distance d, which is 40 megaparsecs in this case, and the alpha t parameter. Okay, and you plug in 1.7 seconds and you find this bound, which has been shown already, that alpha t has to be less than 10 to the minus 15. Okay, and Jutta actually showed this as a two-sided bound, which of course one can do. I thought I'd keep it simple and just work with the absolute magnitude. So as far as we can tell from just one data point, and it's important to stress we only have this one data point at low redshift, alpha t seems to be very, very small and potentially zero. Now, remember I mentioned that the alpha parameters are functions of redshift. And so in principle, one data point, you can't rule out that alpha t has some, very different evolution at higher redshifts and is finely tuned such that it becomes, this very small number just near us. It's a finely tuned example, but it's possible. This is also, I should stress, the most optimistic bound, because this bound assumes that those two signals, gravitational waves and the gamma ray photons, which are the first photons to get out of the merged neutron star, it assumes they set off at exactly the same time. And if you talk to anyone who works on modeling binary neutron star mergers, they'll tell you just how messy things are and that doesn't actually have to be true. So more conservatively, we should allow for a delay of maybe maximum 100 seconds between these two signals setting off. And if we do that, it weakens the bound to about 10 to the minus 13. So weaker by about 2 orders of magnitude. Okay, but it's still a really small number, 10 to the minus 13. And for cosmologists, at least, and as I said at the start, cosmologists and the theories they work on and the regime in which they are testing theories, so these large linearized scales, this ruled out a lot of theories. And I completely take Jutta's point that maybe there are versions of these theories that actually have more interesting phenomenology still on smaller scales. But from the cosmologist viewpoint, this is my sort of traffic light system where I try to show how theories fared under this measurement. And so in red are the things that are completely ruled out. And there's the Fab 4 we saw previously. In green are the things that are completely consistent with that bound. Doesn't mean they aren't strongly constrained by other cosmological observables, but they're at least okay as far as GW 170817 is concerned. Okay, and maybe I should have added F of t gravity on here. Apologies, I couldn't fit that on. And then the things in the middle in orange are somewhere in between. So they're theories that can survive the measurement, but they need to have some extra restrictions imposed on them. As Jutta mentioned, they might have to be a sort of finely tuned balance between some of their parameters, or they might just have some of their more extreme parameter ranges taken away from them. Okay, so this has been big news because anyone building a cosmological modified gravity theory now has to think about how they're going to be consistent with GW 170817. However, there is a slight caveat I should mention. So there was one important kind of loophole that was pointed out about a year after the original announcement, and it came from a paper by Durham and Melville. And they made an argument from kind of very abstract but very general grounds that actually one would expect alpha t, so the difference in the speeds, to reduce to zero at some energy scale. And they argued that that is necessary for a modified theory of gravity to have a Lorentz invariant UV completion. Okay, and when we say UV completion, we're talking about really, you know, if we wanted this to be a candidate low energy theory of a quantum gravity theory, right? We don't know what the quantum gravity theory is, but there are arguments that it has to maintain Lorentz invariance. And so at some point, our low energy effective theory must transition back to that property. Okay, and that's what you're seeing in the graph here. Alpha here is just a parameter. There's a lot of alphas in this talk. And here's the speed of gravitational waves squared. And you can see for different values of this parameter, it can be very low, or could be 2/3, for example. And then at some energy scale, all those speeds transition back to 1. And Durham and Melville argued that this, in Hondesky theories, this transition scale could be as low as about 260 hertz, okay, when you express it as a frequency. It doesn't have to be that low, but it could be. And that's a problem because, of course, GW 170817 merges slightly above that, somewhere in the sort of 300 to upwards hertz regime. And so that's what's being shown here, this argument that if that's the transition scale, you wouldn't expect GW 170817 to find something, and you should still do your tests, i.e. repeat the speed of gravitational wave bounds at lower frequencies with things like the LISA satellite, which I mentioned already, and PTA stands for pulsar timing arrays. Okay, so doubtless when LISA flies, there will be more tests of this kind with the supermassive black hole population. Okay, so that's the sort of the first big thing that happened in this story. The second big thing that happened came from a very different direction. So not from data, but from theory. So you remember when I introduced you to the 5 Hondesky alphas, and the last one I said was called the beyond Hondesky parameter, alpha H, and it told you about this kind of extended family of theories. Okay, and initially following GW 170817, everything was fine, those theories were still in the game. And then this paper appeared, and these authors found that in this extended family of theories, so the one without, alpha H switched on, gravitons, i.e. gravitational waves, can decay into bosons of the Hondesky scalar field. Okay, so they found there were 2 decay channels. They're shown here. It's Feynman diagrams even, if that helps you. And gamma is your graviton, and pi is the boson, the Hondesky scalar. Okay, and this is problematic because gravitational waves are reaching us from hundreds of megaparsecs away now, and they clearly haven't decayed away into our other sources of energy, right? Otherwise they wouldn't reach us. So this seems to kind of cast doubt on whether this extended family of Hondesky models can actually survive. So they found the decay rate. I'm not going to show you all the details in this paper because it's a really long field theory paper. But the one thing I'll show you is the decay rate, which they found in general to be large enough that you would have to worry about it happening on the 100 megaparsec scales we're talking about. So P here is some momentum, lambda stars an energy scale. And the thing that I wanted to show you was this object CS squared, which is the speed of sound or speed of propagation of the Hondesky scalar field. Okay, and you can work out what it is in Hondesky gravity, and it's some big messy expression containing all the alphas, alpha T, alpha B, alpha M, and we don't have to worry about the form here. But you'll notice if we fine tune all the alphas such that CS squared is 1, this decay rate goes to 0, okay, just by Lorentz invariance. And so there is a kind of special case here which could survive this bound. But again, it seems finely tuned unless there's some kind of symmetry argument behind it. And so in general, we would expect CS squared not to be 1, we'd expect this decay to happen. Okay, and the fact that it can't be happening from the observations they used to put a bound on this alpha H parameter. Okay, and as I say, the sort of technical details are in here. But the upshot is that they placed a bound on alpha H purely from theoretical grounds that is less than 10 to the minus 10. So another really tight bound on one of our 5 Hondesky parameters. Okay, so this was quite an eventful 2 years, right? We went from having this 5-dimensional parameter space or functional parameter space that we were testing, and in the space of 18 months, we more or less lost this parameter, subject to everything I said before. We more or less lost this parameter, subject to some kind of loophole that's finely tuned. And so we've got 3 left if we take all those results as valid. And we start asking ourselves then, well, maybe we can actually complete this job. Maybe we can test the remaining 3 parameters. And as I say, either we find something or we've ruled out all of Hondesky gravity. And what I want to do in my remainder of my time is then talk a bit more about the future and methods that are proposed for bounding these 2 parameters, which are the ones I asked you to kind of, save for later. You'll notice that today I am not going to talk about alpha K, and that is because alpha K is the hardest parameter to constrain, because as far as we know at the moment, it only seems to affect observables on the really, really large scales of the universe, so horizon scale observables. And as soon as we look at anything on sub-horizon scales, which is sort of where most of our galaxy surveys are currently probing, it drops out of the equations. So on one hand, that means it doesn't affect anything. So it's not too much of a problem that we can't constrain it. But at the same time, we can't constrain it. So alpha K is a puzzle for the future. Okay. So we are moving on to the 3rd and final section, which is what next? Okay, and in order to talk about what next, I want to talk about gravitational wave propagation equations. Okay, and this is something Jackson also touched upon at the end of his talk. So let's look at the propagation equation for a gravitational wave traveling across an FRW universe in general relativity. Okay, here it is. So Hij is just the linear perturbation of our metric. So it kind of holds the gravitational wave. And we know in reality there's sort of 2 polarization modes hidden within this object, although I won't worry too much about that today. So we have a wave equation here, right? Prime is a derivative with respect to conformal time. I've got a k squared here because I've gone to Fourier space already. So this was a spatial derivative originally. And it's a damped wave equation. We've got a friction term here, which depends on the Hubble factor, or in my time coordinates, the conformal Hubble factor. So somehow, as gravitational waves travel, we expect that the expansion of the universe causes something like a friction, right? Something that's going to damp their amplitude. Okay, so that's the situation in GR. Let's look at what can happen to this equation in modified theories of gravity. Okay, so lots of things can happen. So I've added now 4 new terms to this equation, and I've put them all in color to help them stand out. And I want to stress right away that I'm not talking about any specific gravity theory with this equation. I'm just trying to show you a template of all the places that we could modify. So what's happened? We've got a modification to that friction term, okay, which you'll notice contains alpha m, one of our alpha parameters. I think there's actually a factor of 2 gone wrong there, but not important today. There's that change in the speed of propagation of gravitational waves that we discussed already. That would sit here. There's also the possibility that we have a massive graviton, okay, and that would sit here. There's a non-zero source term that could appear on the right-hand side. Okay, in GR this would be 0, but if we had something that acts like a source of an isotropic stress, it could source this equation. And finally, I can't really show this in the equation here, but there's the possibility of extra polarization modes. Okay, so in GR we just had the plus and the cross polarization, but we could actually have up to 6 known polarization modes in extended theories of gravity. Okay, so there's all sorts of phenomenology here that we could use to test gravity. And currently, these things are in slightly different states of priority and constraint. Okay, so we've seen already that the propagation speed, as we discussed, is really tightly constrained from GW 170817. The mass of the graviton is actually also very tightly bounded from solar system tests. So there's a bit of uncertainty here regarding screening, but assuming it isn't completely screened, the mass of the graviton is bound to be less than an incredibly small number of EV. Conversely, the worst constrained right now are really the polarization modes. And that's because the current LIGO detectors, the way they're constructed, they're very bad at measuring polarization. So we really need future detectors to get a handle on that. The source term that I mentioned is actually quite rare in the sense that most modified gravity theories don't cause that term to arise. There's only a small handful that I know of, things like bigravity that cause that term. But the most generic term is the one sitting here. So it is that modification to the friction that potentially could affect your gravitational wave amplitude that crops up in all kinds of theories. Okay, and so what we'll do is we'll focus on this term today as the most sort of relevant one. Okay, so I've taken away the others just to unclutter things. So what's this going to do to our gravitational wave? Okay, we can work that out by doing a really sort of quick solution of this equation. So to keep life easy, I'm going to sort of forget about polarization today. I'm going to pull off that into some polarization tensor EIJ, and we'll just focus on this sort of amplitude H. And we'll write H as equal to some GR value, whatever the GR prediction is, and we'll allow it to be modified by a factor B. And potentially we should allow for a change to the phase of the gravitational wave, which we'll call C. Okay, so you can plug this into the equation here. You can do a WKB approximation and solve to get your factors B and C. Okay, and what you find, C is 0, so there's no phase shift in this particular equation, so that's fine. But B is non-zero. What you get for this factor B is an exponential, and the argument of that exponential contains the time integrated alpha m. Okay, so remember I said these alpha parameters are actually functions of redshift, and somehow there's this kind of integration over the history of alpha m that is going to change the amplitude of your gravitational wave. That's all fine, but to make progress, we need to know what is the GR prediction in the first place. Okay, and luckily that's a well-studied bit of physics, at least at lowest PN order. So, you know, the simplest approximation for early stage inspirals, and today, keep it simple, a circular inspiraling binary. The amplitude of your gravitational wave in GR would be given by this, okay? So it contains the chirp mass with some power, the frequency with some power, and in principle, there should also be a polarization factor in here. We won't worry about that. Importantly for us, what sits in the denominator here is the luminosity distance to the gravitational wave source. Okay, luminosity distance is just one of our standard cosmological distance measures. And for a flat cosmology, which is all I'm interested in today, it's just the co-moving distance multiplied by a factor of 1 plus z. So that's the GR prediction, but we said that's going to get multiplied through by this exponential factor. So let's do that and let's see what happens here. Okay, the most natural thing when we multiply this through, it can't really be absorbed into the mass or the frequency because of the power law dependence, but that modification could quite easily sort of be absorbed into a redefinition of the luminosity distance to the gravitational wave source. And now we have this new effective luminosity distance that is its original value, the standard luminosity distance, which is the one you would get from photons. But now it's been modified by this kind of factor, this new factor that depends on our modified gravity parameters. And if we can then find sources that have electromagnetic counterparts, what we often call standard sirens, we could hope to measure the blue dGW from the gravitational wave. We can measure the yellow luminosity distance from the electromagnetic counterpart, and we could hope to bound the parameters that sit in the middle. So just to show you some kind of quick plots to guide the eye on how this behaves, I've got here a plot showing the ratio of those two distances in a selection of Hondesky theories. Okay, and I'm just playing about with the parameter alpha n here. You can ignore this second column of alpha b for now. And so, of course, in GR, this ratio would just be 1 for all redshifts. And what you see is that depending on the parameter values here, we get this slip that grows with redshift. We get this difference between these two distances. Okay, and behind the scenes here, I've had to assume some particular redshift dependence of the alpha n parameter, but that's just a modeling choice I have to make to draw a plot. I've got some data points on here, or rather I've got some mock data points on here, and there's only one real data point, which is of course from GW 170817. That's the only object we've detected so far that has a confirmed electromagnetic counterpart. Unfortunately, that event was at really low redshift, too low to really be sensitive to the slip in these different distances. These small points here, that's a sample of 100 mock events for things like GW 170817 that could be detected over the next 5 to 10 years. And it's really these points I'm interested in. This is a forecaster of mock LISA data. And remember, LISA is observing massive black holes at the center of galaxies. And because those objects are so massive, they produce larger amplitudes of gravitational waves. And that means that they can potentially be detected out to much higher distances than the kind of stellar mass sources. And so it's really these things that have then the potential to give the greatest constraints on our ratio here and tell us about modified gravity. So we want to get an understanding more quantitatively of how well could we measure our remaining alphas with LISA. And I've spent a large part of the past year trying to understand all the things that go into building mock data for LISA. And you'll be relieved to hear I'm not going to tell you about all of that. I'll tell you just two quick things, I think. Okay, so two things you have to worry about here. First of all, you have to worry about the population of massive black holes and where on earth it comes from. Okay, we are still uncertain on an astrophysical level what seeds those massive black holes and allows them to grow so large by the universe today. Okay, and there are several sort of theories on the table. One of them is called the light seed family of models. And this includes things like the collapse of population 3 stars. So the first stars in the universe, they're really massive, 300 solar masses. And it's the idea that they collapse to form black holes of about 200 solar masses at redshift 15 to 20. And those things then accrete over time and become the massive black holes we know today. Okay, and we'll call that the POP3 model. The sort of counterpart to that, not surprisingly, is called the heavy seed family of models. And in these models, the seed black holes come not from collapse of stars, but from the collapse of protogalactic disks themselves. Okay, and they form much larger seed black holes, hence the name, which again grow to become the black holes we know today. And there's a sort of key outstanding question in these heavy seed models. What happens when two host galaxies merge? Okay, like this beautiful picture of the mice galaxies, these are two merging galaxies, and when they finally merge over millions or billions of years, will their central black holes merge as well straight away? Or will they enter some kind of stable state in a binary and you'll have a merged galaxy with a binary massive black hole in the center? And if they merge straight away, we call that no delay model. And if they stall and essentially take another few billion years to merge, we'll call that delay. Okay, the reason this matters is because this has potentially a huge effect on the number of events LISA will see that we can use. Okay, so just to show you this, this is some of the catalogs that I spent a long time producing. On the left, you've got that POP3 model, the light seeds, and I'm showing you detections that LISA would make over a 4-year mission lifetime, and they're shown in mass and redshift, and they're color-coded by the signal to noise of the detection. Compare that to what happens in the delay model, where we have many, many fewer mergers. As a result, there are only about 30 detections in a 4-year mission. Okay, so clearly the outcome on the right is going to be much harder to perform, really good tests of gravity with, because we have less data. So that's one thing you have to worry about and model. The second thing I'll mention just briefly is, on top of this, you have to ask how many of these massive black hole mergers actually have detectable electromagnetic counterparts, right? And by electromagnetic counterparts in this context, we're thinking of some kind of flaring in the center of the galaxy, maybe some quasar activity or AGN activity caused by gas in the center of the galaxy that's getting shocked and heated in the merger. And it's quite low. It depends on the model, but for POP3, for example, it's around 10% of events that are expected to have something like that. We don't actually know for certain. So in light blue here is my catalogue of POP3 events, and in dark blue are the selected ones that have an EM counterpart. Okay, so it's an even smaller sample. And what I've done here is I've distributed the electromagnetic counterparts in some sensible way, because of course we're more likely to observe the ones at low redshift than we are at really high redshift. Okay, you also have to worry about inclination of your binaries, but I think in the interest of time, I will skip that today, and I'll just show you the results.
Sorry, apologies, Tessa. We have 5 minutes. That's fine.
5 minutes. Okay, yeah, great. Thanks. So let's get to the results then, if we've got 5 minutes. So we're going to use that mock LISA sources to constrain alpha n. And we're also going to combine that with a lot of standard cosmological observables. So things like the CMB, Galaxy surveys that constrain alpha M, but also our alpha B parameter. Okay, and I didn't talk about this today because I wanted to focus on the gravitational waves. But in a nutshell, things like the CMB and things like the growth rate of structure have an additional sensitivity to alpha B. And you'll notice that you can build Hondesky models like this one in light blue that is actually really close to the Planck data points, fits that really well, but gives huge discrepancies in the growth rate of structure. Okay, and that's why you want to combine as many data sets as possible, is to really break that kind of degeneracy. So I'll throw some EM data into the mix, and I'll use existing surveys and supernovae. Okay, and here we go then. That's the sort of final forecast results we get, in this case for the POP3 model. And what you're seeing here is constraints on your two parameters, so alpha M and alpha B. And actually you're seeing their values at redshift 0 here, where I've assumed some redshift dependence. And what you see in blue in the background is the constraint you would get from large-scale structure data alone. In green is what happens when we add those LIGO sources, the stellar mass binaries, which, as you can see, don't have a huge effect because they're too nearby. And in red is what happens when we add in that LISA data. And you can see it really shrinks down the constraints on that alpha M parameter. So the forecast constraint for those is something around the 0.1 mark. And you can see there's some kind of funny shape going on here. That comes from stability bounds. So this solid line basically comes from the fact that we know Hondesky models that sit below here are unstable to pathologies. There's a sort of weaker bound that comes from the growth of large-scale structure up here, because if alpha M is too large, structure forms too much. And what the gravitational waves are doing, as I say, is they're squeezing this contour in top and bottom. Okay, I will skip the next slide just to keep to time. So the final thing I need to do, and this is my last slide, is, well, apart from conclusions, is tell you how good these constraints are. Because I said we could bound the alpha parameters to 0.1 for alpha M, maybe slightly larger for alpha B. But how good is that? Okay, so if we tried to do this analysis with just one binary neutron star, you would bound the alpha parameters to about 10, so it would be huge. If you try and do it with that 100 binary neutron stars, you get them to about order unity. And that's about the same as we do with current large-scale structure data, so things that are available today. What we really want to do, though, of course, is think about the large-scale structure surveys that will be available at the time that LISA flies. Now, we can't actually project ahead quite that far, but we can think about the next generation of large-scale structure surveys. So things like the LSST or the Vera Rubin Observatory now, and they bound the alphas by themselves to about 0.2. So this is a projection because we haven't done the analysis, but the hope is that with future large-scale structure and future gravitational waves, you'll bound these alpha parameters maybe down to about 0.01. And the hope is that that's a level which really starts to be challenging for theorists, right? As I say, either we find something or this then becomes something that really drives the theoretical community forward to build different kinds of gravity models and hopefully things that spark new ideas and hopefully lead us closer to a solution to the dark energy problem. All right, I will leave it there today. Just my quick visual summary of the alphas. I introduced you to these 5 parameters. I said this one was ruled out by the speed of gravitational waves, more or less. This one was ruled out by theoretical ideas, more or less. This one, we said we couldn't really constrain with current observables. And hopefully I convinced you that these two can be bound by a mixture of gravitational wave luminosity distances and EM data. And our hope is to close off this Hondesky parameter space. All right, I'll leave it there. Thank you for your attention, and I'll happily take any questions.
Okay, Tessa, thank you very much for your wonderful talk. And we already have questions. Salvatore, if you want, go ahead with your microphone. That's fine.
Okay. Hello, Tessa. Thank you very much for this very nice presentation. I have two. I would like to have a comment by you, and the comment is this. Do you believe that Hondesky is on the ground after the fact that they claim that they have ruled out in the paper by Lombrosier and the others, they say that Hondesky is ruled out. But according to your talk, it seems that there is a lot of possibilities for Hondesky. What is your impression? What is your feeling?
So when you say the Lombrosier paper, do you mean the one about that suggests that it might be hard to detect this luminosity distance effect? Right.
Yeah, okay, exactly this.
So the claim by Lombrosier et al. Is that essentially when you've taken account of the fact that a gravitational wave has to travel, across space to us and then back into a galaxy, i.e. potentially a screened regime, that ultimately, because your detector sits in a screened regime, you lose this effect of a running Planck mass, right? Which was effectively what alpha M was measuring. So they have shown that explicitly in certain screening mechanisms. So to be fair, they have shown it in Weinstein and chameleon, which are the two biggest screening mechanisms on the market. So definitely, if you have a Weinstein screen theory, this observable is not going to work for you. However, that's not the same as saying Hondesky itself is ruled out. That's just, first of all, that's a statement about a particular subclass of theories. And secondly, it's a statement that you can't measure the effect, not that it doesn't exist. Does that make sense?
Yeah. Thank you very much.
So the general framework still holds, but the points are interesting.
Yeah. Thank you. I agree completely with this vision. Thank you.
Okay, perfect. We have another question from Mariana Haber. Do you want to go ahead, Mariana?
Yes, thank you. And thank you for the great lecture. The first one, it's actually related to the one by Professor Salvatore. I think you actually kind of answered it already, because it was regarding about how to implement the screening mechanisms on the use of this observable to constrain alpha M. So I think it's an issue of taking more carefully the specific model and the specific type of screening, right?
Yeah. The alphas are really only a parameterization of the linearized physics. And so you require a model by model analysis to really get the screening.
And the second one is just you showed this plot where you are modeling different populations of events. And I could see that you go as high as redshift 15, even for events without an electromagnetic counterpart. So I was wondering, how can you estimate these events without the electromagnetic counterpart? I mean, how can you model them? We don't have surveys like Galaxy surveys going that high. Even at redshift 1, I think completeness is already an issue. So I was wondering, how can you do these estimates? Thank you.
Yeah, thanks for that. So that's a very good point. So I showed you these populations of sources going out to redshift 15 or even redshift 20. That is for the gravitational wave component alone. And so those detections where it was 600 or so, that's just the gravitational waves. And then when we're talking about EM counterparts, I said actually only maybe 10% of these, maybe 20, depending on the model, have an EM counterpart. And you're absolutely right that the 20%, sorry, I should say that it's the 20% that is detectable, and the 20% that are detectable, or 10%, are of course very much skewed towards the lower redshifts. And I certainly don't expect us to be detecting electromagnetic counterparts at redshift 15 or anything like that. There is some debate in the LISA community, but we think there is potentially a sweet spot somewhere around a redshift of a few, where the change caused by modified gravity is large enough to be detected, but there is still a chance of seeing the EM counterparts. And you're absolutely right that, of course, completeness is awful at redshift 2 or 3, but it's a case that we think these events should be very bright and also very variable. And so it would really be a case of relying on finding galaxies that are changing or doing something very luminous. And you're right, there'll be ones of them that we would miss for sure. So that, yeah, more work is needed to find exactly what is that sweet spot and can we make it work between those two competing factors of modified gravity effects and detectability.
Thank you so much.
No worries.
Okay, great, thanks. Tessa, if you allow me, I have a question also for my part.
Yeah, sure.
Also, I have been working with the same catalogs. Yeah, you already have this POP3 and with the heavy and this kind of a scenario. But I want to know, I mean, your opinion about, because the catalog with the heavy seeds is have two counterparts, one with pessimist and another with optimist scenarios. In the case that you don't have this problem, no, with the extra signal. In this case for Hondesky, because I put it an extra dimensional theory, and specific I used a DGP theory, is if I can prove there is some gravitational leakage in some extra dimension. But in Hondesky, how can we measure this pessimist? Because that is the problem, no? With the pessimist scenario, when you don't have this noise for this forecast that you are performing.
I'm not sure I fully understand. So certainly the paper that I use to get EM counterparts, which is the Tamanini one, has a kind of pessimistic and optimistic one. And I think it's not quite a factor of 2, but it's roughly a factor of 2.
Yes, indeed.
Between them. Yeah, and I think we actually study both in the paper. I think I've shown you the optimistic ones today because they look better on plots, but sure, it will weaken the constraints.
Yes,
but
because sorry. Go ahead. No, sorry.
So I've been listening to a lot of talks over the past few years, and the Tamanini paper, which I originally took as kind of a reference, compared to other talks, actually seems quite pessimistic in general. At one point, I got very depressed that we'd done all this work and actually the constraints were going to be quite bad. But then other people who talk more about the real kind of digging into the astrophysics of what's actually going on around these supermassive black holes seem to be more optimistic. So I'm an observer in this community, and I'm getting slightly mixed responses. So I wonder if that's something you've come across as well.
Yeah, for sure. Maybe we should talk about this because we have a very optimistic scenario for this thing. So maybe it can be useful for Hondesky as well. Yeah, sure. Thank you very much. So I think there is not more questions. So thank you very much, Tessa, for this nice talk. Well, probably we'll see you tomorrow as well. And thank you.